Lowering the exposure time can significantly destabilize the printed dental prosthetics, potentially leading to print failures.
Hello everyone, thank you for joining us today. My name is Jenny. Happy New Year everyone! So today we have a start with Dr. Kim, who always gives us the best lecture. Thank you for being here, Dr. Kim.
Hi Jenny and welcome everyone. As we begin the new year of 2024, I wish you all a healthy and happy new year.
Thank you, Doctor. And thank you everyone for joining us today for the webinars. I can feel your eagerness to learn more about digital dentistry with Medit. I'm sure Dr. Kim will give us another useful and interesting lecture for today's webinar, right?
Yes, I had prepared all about printing. It is going to be a powerful tool if you are able to deal with printing work in your daily practice. You will experience your treatment workflow become simple and easy. So I would like to emphasize how much profile validation is important and share my clinical tips to resolve dimensional inaccuracy in 3D printed crowns by improving profile validation.
Yeah, I heard that printing technology is highly useful in the clinics, but it's really hard to have a perfect prosthetic fit. I hope everyone would be able to have a perfect prosthetic fit through this lecture. And time flies, it's already fourth webinar in our huge series of reducing chair time.
Yes, right. Let's get it started.
Okay.
Welcome everyone, and thank you for joining us in the fourth lecture of our Reducing Chair Time for Dental Crowns series. Today, we will focus on identifying and resolving challenges associated with 3D printing in dental crown production, aiming to significantly reduce treatment time. We will explore various solutions to enhance the efficiency and reliability of 3D printed dental crowns. I am excited to share insights on overcoming these technical hurdles and how these improvements can lead to more efficient dental treatments. Let's embark on this journey to advance dental care through innovative problem solving in 3D printing technology. In this lecture, we'll discuss the issue of dimensional inaccuracy in 3D printed dental crowns. Specifically, we'll address how the jelly effect and light bleeding contribute to this problem, along with polymer shrinkage. These factors can lead to a misfit of the crown on the patient's tooth. We will explore technical solutions to prevent these issues and to produce crowns with precise dimensions. In this section, we'll focus on the critical strategy of validating and improving the profile to resolve dimensional inaccuracies in 3D printed dental crowns. We'll begin by emphasizing the importance of profile validation and how it leads to improvements in dimensional accuracy. We'll also examine the technical adjustments needed to enhance the profile and explain how these adjustments positively impact the quality of the crowns. Through actual case studies, we'll demonstrate the effectiveness of this approach. Our viewers will get a clear understanding of why profile validation and improvement are crucial in the 3D printing of dental crowns. This information will be invaluable for dental practitioners using 3D printing technology to produce more accurate and reliable dental crowns. In this slide, we will define what a profile is in the context of 3D printing and why it is crucial for the production of dental crowns. A profile is a configuration file that contains all the detailed settings of the 3D printing process. These settings determine factors such as the printer's speed, temperature, layer thickness, and exposure time. Proper profile settings can significantly enhance the accuracy and quality of the printing process. For dental crowns, this means providing better fit and functionality for the patient. We will examine the key components of a profile and discuss how these elements impact the quality of the final product. In this section, we will explore the key factors that influence the 3D printing profile, which directly affect the quality and efficiency of printing. 1. type of resin. There are various types of resins available in the market, each with its unique properties. For instance, differences in transparency, heat resistance, and strength among resins can significantly impact the performance and application of the final product. 2. Resin photopolymerization speed and strength. The intensity of the light used during printing and the exposure time greatly influence the curing speed and final properties of the resin. This is a critical factor in determining the durability and quality of the product. 3. Layer height and speed. These settings determine the thickness of each layer that the printer will produce and the printing speed. Balancing these aspects is crucial for achieving a trade-off between print precision and speed. 4. Support structures. These settings are essential for ensuring that the model is adequately supported and printed stably. Inadequate support structures can lead to print failures. 5. Additional settings. Depending on the printer model, the brand and type of resin used, and environmental conditions, additional settings may be required. All these factors play a significant role in the optimization of the profile. In this lecture, we will focus on finding the optimal settings for the 3D printing process, which are crucial for the quality and accuracy of the printed products. 1. Layer thickness. This refers to the height of each layer produced by the printer. Thinner layers allow for more detailed resolution, but can increase the printing time. 2. Exposure time. This is the duration for which the resin is exposed to light, affecting the curing speed and the strength of the final product. 3. Scaling. This setting adjusts the size of the model, which is critical for ensuring dimensional accuracy. 4. Over-extrusion compensation. This compensates for any dimensional inaccuracies that may occur during the printing process, improving the final product's dimensional accuracy. 5. Delay. This is the time allowed after printing a layer. For the movement of the resin in the vat, this step is crucial for optimizing print quality. 6. Build plate movement speed and distance. These settings determine the movement speed and distance of the print head, impacting the efficiency and quality of the printing process. Resin profiles are often provided by 3D printer manufacturers or the community, and you can use them to optimize the performance and quality of your model. Depending on your printer and resin type, you can choose the best profile to achieve the desired output results. Below are a few ways to find resin profiles. 1. 3D printer manufacturers. You can visit your 3D printer manufacturer's website to find the resin profile for your model. Manufacturers often provide settings that are compatible with their products. 2. The resin manufacturers. You can also find profiles for your type of resin on the resin manufacturer's website. Manufacturers often provide settings that optimize their resins. 3. Online 3D printer communities. You can search the internet for 3D printer communities and forums to find resin profiles shared by other users. These communities share different settings and experiences and can be a great source of information. 4. 3D printer software. Some 3D printer software may have resin profiles built in. You can use the profiles provided by your printer software to easily adjust your print settings. Before using a profile, you should find one that fits your 3D printer model and the type of resin you will be using. Follow the manufacturer's instructions before using the settings and make adjustments if necessary based on the experience of other users. If a resin profile is not available, you can still create one and optimize it. To do so, you'll need to follow a few steps. 1. Know the basics. First, you need to know the basic characteristics of your 3D printer and the resin you want to use. You should be able to get information such as the resin's curing speed, layer height, etc. 2. Test and tweak. Create a small experimental model or test print and print it with different settings. This will allow you to see which settings work best. Analyze the output by adjusting layer resolution, exposure time, print speed, etc. 3. Invest time and effort. The process of creating a profile takes time and effort. You'll need to experiment and adjust multiple times to find the optimal settings. 4. Share your experience with the community. You can share your opinions and experiences with other users in 3D printer communities or forums. You can get advice and help from others to further improve your resin profile. 5. Utilize software. Some 3D printer software may offer the ability to create profiles directly. You can utilize this to create and apply custom profiles. 6. Make incremental improvements. It can be difficult to create the perfect profile at first. However, you can gradually improve your settings and improve the quality of your output. It is important to keep improving through experimentation and tweaking. In a light curing resin 3D printer, layer thickness refers to the thickness of each layer during the printing process. It's one of the most important factors in 3D printing. Photopolymer resin printers use light to cure liquid resin to build objects layer by layer. The thickness of each layer greatly affects the resolution and surface finish of the final print. Small layer thickness provides finer detail and a smoother surface finish, but can result in longer print times. Large layer thickness can reduce print time, but can result in a rougher surface and reduced detail. Layer thickness is typically measured in microns and can be adjusted based on specific printer and project requirements. To break it down a bit further, stacking thickness refers to the resolution in the z-axis direction. Changing the stack thickness has the following implications. For example, let's say you want to output a 10 mm thick model. If the output thickness is 100 microns, it will be sliced into 100 layers. The light exposure time for each layer will vary depending on the material, but let's say 5 seconds. After exposure, the plate movement time and waiting time required to peel off the print with film is about 10 seconds. The total print time is expected to be around 25 minutes. The surface of the printout will have noticeable layer boundaries. If we change the output thickness to 50 microns, we will be slicing into 200 layers. Since the thickness is halved, you would think that the irradiation time is also halved, 2.5 seconds, but around 60 to 70% is typical. So let's say 3.5 seconds. The plate movement time of the plate remains unchanged at 10 seconds. The total output time is expected to be around 45 minutes, an 80% increase. Thinning the output thickness increases the time, but the main benefit is the improved surface texture. With a 100 microns layer, the lines are clearly visible. This setting can be used to quickly create temporary teeth and guides. A 50 microns layer thickness makes layer lines less pronounced, which is a good choice for most common models. This thickness provides a balance of fast print time and adequate detail. On the other hand, a 20 microns layer thickness is very detailed, with layer lines almost invisible and a glossy surface. Such high-resolution printing is particularly suitable for final prosthesis output, providing an excellent surface finish. Therefore, it is important to choose the right layer thickness based on the type of prosthesis and its requirements. Layer thickness directly affects the z-axis resolution, and for final prostheses, we recommend a 20 micron stacking thickness for high z-axis resolution. It is necessary to match the XY resolution similarly. Here we used a printer with an XY resolution of 22 microns. These precise settings contribute to a significant improvement in the accuracy and appearance of the prosthesis. This slide discusses the fact that varying the layer thickness does not significantly affect the quality of the 3D printed output. This suggests that, contrary to popular belief, under proper printing conditions, changes in layer thickness may not have a significant impact on the quality of the final output. Therefore, optimization of other setup factors is required to improve quality. Delving further into the 3D printing process, let's explore the crucial role of exposure time, especially in the context of dental crown fabrication. Exposure time is all about the duration for which the resin is exposed to light, a key factor in determining the resin's curing speed and depth. The selection of the right exposure time is critical for the final product's strength and durability. Inadequate exposure may result in resin not curing fully, compromising the strength of the end product. Conversely, overly prolonged exposure can be counterproductive, leading to unnecessary energy consumption and potential distortions. Adapting the exposure time to suit the specifics of each project, as well as the resin type in use, is an essential step in the printing process. Often, this involves conducting several trials to pinpoint the most effective exposure settings. Exploring the factors that impact exposure time provides insightful understanding into how these elements influence the 3D printing process, especially in terms of resin curing and the quality of the final output. Exposure time, the duration for which the resin is exposed to light, is a critical aspect of the printing process. Key influencing factors include the type of resin, the intensity of light, printer accuracy, and the environmental conditions, such as temperature and humidity. Each factor plays a significant role in optimizing exposure time. For instance, different types of resin may require varying exposure times, and the intensity of light and printer precision directly affect the uniform curing of the resin. Additionally, temperature significantly impacts the reaction and curing rate of the resin, necessitating adjustments in exposure time settings. In this part, we examine two test models to understand how specific settings in the 3D printing process impact the final output. These models visually demonstrate the importance of fine-tuning various printing parameters. The first model showcases the effect of exposure time settings on the surface finish and detail of the output. It provides insights into how exposure time influences the quality of the final product, emphasizing the importance of optimizing exposure time for resin curing and quality. The second model illustrates how support structure settings affect the support and output of complex structures. This model highlights the necessity of optimizing support structures to enhance stability and structural integrity during the printing process. Through these models, we gain a deeper understanding of the significance of each setting in the 3D printing process and develop strategies for achieving optimal printing results. On this page, we introduce a unique test model where the clarity of the text is the primary focus. This model visually demonstrates how to optimize the fine details and clarity of text in the 3D printing process. Composed entirely of text, this model is useful for quickly finding exposure times that enhance the clarity and readability of text. Let's walk you through how to adjust the exposure time in your slicing software for 3D printing. First, open your slicing software. This software is where you convert your 3D model into layers and instructions for your printer. After loading your model, go to the Print Settings panel. This is where you'll find the exposure time setting, which is usually under the Resin or Material Settings tab. Make your adjustments and save your settings. We recommend doing a test print to see the effect of your changes. Once the print is complete, clean the model. This is an important step to remove any residual resin and bring out more detail in the print. After cleaning, closely inspect the writing for clarity and accuracy. Only at this point can you accurately assess the detail and legibility of the writing. The objective of this stage is to produce clear and readable text through 3D printing. The key to success lies in the precise adjustment of exposure time, as both overexposure and underexposure can significantly affect the text's clarity. There are 3 photographs that demonstrate the importance of fine-tuning exposure time. The central photo represents a perfect outcome where the text is crisp and accurately rendered. On the left, you'll see a photo of blurred text, a result of overexposure. In this case, letters such as E may appear filled in. The right photo illustrates missing text, a consequence of underexposure, where finer details like the dot of an I might be missing. This test model features a central connection point reminiscent of an hourglass, with varying thicknesses. This design element emphasizes how different thicknesses can withstand varying levels of stress, showcasing the impact of exposure time settings on structural strength. The varying thicknesses in this hourglass-shaped connection visually demonstrate how different exposure times can affect the model's structural integrity and durability. This serves as an excellent example of the importance of fine-tuning in the 3D printing process, clearly illustrating how exposure time influences structural stability and the endurance of the product. Let's now analyze the results of our test model. We will compare the successful outcomes with the failures to deduce the optimal exposure time. Looking at the successful side of the results, we generally see well-maintained strength in the connections, but a notable failure is observed in sample number 4. This indicates that the exposure time was insufficient for this sample. However, using the first letter test model, such failures as in sample 4 are unlikely to occur. On the failure side, sample 1 shows some successful connections, while sample 2 barely failed, and samples 3 and 4 almost didn't print at all. This suggests that sample 1 had excessive exposure, sample 2 had the optimal exposure time, and samples 3 and 4 suffered from insufficient exposure. Based on this analysis, we should fine-tune the exposure time until we achieve results similar to sample 2, incrementally increasing or decreasing the exposure time to find the perfect balance is key. This process will allow us to determine the most suitable exposure time for a specific project. Now that we have finely tuned the exposure time, we will proceed to print an actual crown to validate the effectiveness of our settings. The process will be carried out as follows, ensuring we thoroughly assess the quality of the 3D printed crown. First, we select a crown design from Medit link. This design is then integrated with slicing software to be transformed into a printable file. In the slicing software, we set the position and orientation of the crown. This step involves determining the optimal printing placement and direction for the crown, and adding necessary supports to create the output file. Once the crown is printed, we remove the supports and proceed with cleaning. The post-curing process follows, enhancing the strength and finish of the crown. We have now successfully printed a crown using the determined exposure time. However, to ensure the crown is suitable for clinical use, several issues must be addressed. We will demonstrate the process of identifying and resolving these issues. The first issue to address is that the crown may not have printed exactly as originally designed. While exposure time plays a critical role in successful printing, it's not the sole factor. For the prosthetic to be fully functional and fit correctly, it must be printed to the precise design specifications in terms of volume and size. To validate this, we will proceed as follows. 3. Result analysis. *. Through this comparative analysis, we will evaluate the accuracy and functionality of the crown. This step is crucial in determining if the printed crown is suitable for actual clinical use. This process will enhance the quality of the printed crown and ensure it reaches a level suitable for clinical application. Such verification is vital in increasing the accuracy and reliability of dental prosthetics produced using 3D printing technology. The printed crown will be scanned to precisely measure its actual size and shape. The scan data will be aligned with the Medit design to analyze any discrepancies from the original design. Through this comparative analysis, we will evaluate the accuracy and functionality of the crown. On this page, we will delve into the analysis and explanation of the verification results for the printed crown. Comparing the scanned data of the crown with the original design, significant discrepancies were noted, particularly in the interior, exterior, and occlusal surfaces. For the crown's interior, we observed a narrowing result due to polymerization shrinkage, which deviates from the original design. This affects the precise fitting with the patient's tooth and directly impacts the comfort and functionality of the crown. On the exterior, the differences from the design are less pronounced, but discrepancies are still observed in certain areas. These can affect the crown's appearance and the patient's aesthetic satisfaction. The most critical errors were found in the occlusal surface. Accuracy in this area directly influences the patient's bite stability and chewing function, necessitating significant improvement in these discrepancies. We are now beginning the process of addressing one of the previously identified issues in the 3D printing of crowns: the XY plane printing inaccuracies. In this phase, we will focus on tackling the problems of polymerization shrinkage and over-extrusion. Polymerization shrinkage occurs during the curing process when the resin volume decreases, leading to the crown dimensions being smaller than the original design. Over-extrusion, on the other hand, happens when the printer outputs more resin than necessary, resulting in the crown being thicker than designed. Therefore, it's essential to find a balance that considers both these issues, polymerization shrinkage and over-extrusion, to achieve the optimal printing result. In this presentation, we will explore how to identify and resolve these issues, offering strategies for overcoming the challenges of polymerization shrinkage and over-extrusion. In this section, we will discuss a significant issue in 3D printing: polymerization shrinkage. This is an inherent characteristic of 3D printing resins, where the volume of the resin decreases during the curing process. One way to address this issue is by adjusting the print scaling. By applying a scale adjustment proportional to the XY dimensions of the print, we can compensate for the dimensional inaccuracies caused by polymerization shrinkage. This step is crucial for enhancing the accuracy of the printed crown. However, there's another factor to consider while addressing the problem of polymerization shrinkage. As I mentioned earlier, this involves the commonly encountered issue in 3D printing: over-extrusion. This phenomenon occurs when an excess amount of resin is printed, leading to the crown being thicker than intended. Over-extrusion occurs when more material is printed out to the sides than is necessary during the printing process. Over-extrusion often occurs when the printer's material has a high viscosity or if the waiting time between layers is too short. This issue arises from the printer dispensing too much resin or dispensing it too rapidly, necessitating adjustments in printer settings. Additionally, the excess material in over-extrusion tends to have a consistent absolute value regardless of the model's size. This means that similar patterns of over-extrusion can be experienced across models of different sizes. In this section, we will discuss the phenomenon of light bleeding in 3D printing. Light bleeding occurs when the light source in the 3D printer spreads beyond the intended boundaries of the model, causing adjacent resin to cure unnecessarily. As a result, the sides of the model can become thicker than intended. This spread of light happens during the photopolymerization process, as the light affects the resin beyond its intended range, which can negatively impact the model's accuracy and detail. To reduce light bleeding, one approach is to adjust the exposure time. By setting the appropriate exposure time, it's possible to minimize the unnecessary curing of resin. Additionally, using a more precise light source can also help in reducing light bleeding. In this section, we will discuss the jelly effect, a phenomenon particularly prevalent in 3D printing using photopolymerization resins. The jelly effect is attributed to the viscosity of the material. It occurs when the build plate moves after the start of photopolymerization, causing gel-like resin to push out and form layers thicker on the sides than anticipated. This effect can arise due to the precision movements of the printer's axis or the physical properties of the resin. Minimizing the jelly effect is crucial as it can impact the accuracy and quality of the printing. One way to reduce this effect is by lowering the viscosity of the resin. Additionally, adjusting the printing speed and the delay can help control the flow of the resin more effectively. In this section, we will address a specific issue that arises when printing black-colored models using 3D printing technology. When printing in black, two simultaneous phenomena occur. The first is the model shrinking and appearing in a dark gray shade, and the second is the outer part of the model becoming thicker and lighter in gray. These opposing effects can mix, leading to an underestimation of the shrinkage values when only considering polymerization shrinkage. Therefore, accurately identifying and measuring both shrinkage and overextrusion simultaneously becomes challenging when printing solid-filled models and only assessing the external dimensions. This limitation can lead to misinterpretation, where the actual impact of shrinkage and overextrusion on the model may not be fully understood. Therefore, to accurately assess both polymerization shrinkage and overextrusion issues, measurements in different directions are necessary. To achieve this, we recommend printing a model with a hollow interior, allowing us to simultaneously check for discrepancies both inside and outside. Polymerization shrinkage causes both the interior and exterior of the model to shrink inward. In contrast, overextrusion results in the exterior expanding outward while the interior thickens inward. In the previous section, we mentioned that the amount of overextrusion is constant regardless of the output size. Now, assuming that polymerization shrinkage has been compensated for with the correct scaling, we can focus on the overextrusion problem. In this case, the overextrusion will thicken to a uniform value inside and outside the model, which is represented by the light gray areas in the figure. In this section, I would like to introduce a test model that I have designed and use specifically for accurately measuring and understanding polymerization shrinkage and overextrusion. This model is crafted to precisely evaluate these phenomena in 3D printing. By printing this model at various scales, we aim to find the point at which the discrepancy between the interior and exterior dimensions of the model is minimized. As seen in the image on the right, our goal is to identify the scale at which the error values of the inner and outer surfaces become similar. The scale applied at this point represents the magnification needed to compensate for polymerization shrinkage, ensuring that the model is printed true to its design. Furthermore, the value of the error protruding outward indicates the amount of overextrusion. By quantifying this, we can adjust the printer settings to minimize overextrusion. We'll discuss the effective scaling to start with in 3D printing. Given that all resins shrink, it's more efficient to start with a scale slightly higher than 1.000, such as 1.007. There are various ways to apply scaling in slicing software. The first method is to modify the scale of the print directly. However, this is not recommended as it requires adjustments for every print. The second method involves modifying the expansion scale in the profile. This approach is more efficient as once set, it applies to all prints. The third method is useful if the slicing software doesn't provide the option to modify the profile's expansion scale. In such cases, you can adjust by dividing the LCD size by the desired scale. In this section, we will focus on the scanning process, which is crucial for verifying the accuracy of 3D printed models. Initially, we print the model with the set scale, followed by a post-curing process. An important step to note is the cooling time post-curing, which is essential for the model to stabilize and for its final dimensions to be established. Although using a model scanner is the most accurate method for scanning, a dental scanner can also be employed effectively. We recommend placing the model on a turntable and securing the scanner for this process. In this section, we will discuss the process of comparing the scanned file with the original model file. First, both the scanned file and the original model file are uploaded to Medit link. Then, we launch Medit Design and load both files. We use the alignment mode to align the two models. After alignment, we examine the deviation patterns using the deviation display feature. If the applied expansion scale was insufficient, the inward-facing surfaces of the model will appear thicker than the outward-facing surfaces. Conversely, if the scale was too high, the opposite will be observed. Upon identifying these differences, we move to the transformation mode to adjust the XY scale. In this case, as the scale was insufficient, we incrementally increase it by 0.001 and observe the results. This process is repeated until the discrepancies between the inside and outside of the model are similar. The number of adjustments made is then added to the original print scale to calculate the modified expansion scale. For instance, if 5 adjustments were necessary, we add 0.005 to the original scale of 1.007, resulting in a final modified scale of 1.012. In the attached images, we showcase the results of our 3D printing accuracy tests with different expansion scales. The left image represents the outcome of a model printed with a 1.012 expansion scale, while the right image shows the result of a model printed with a slightly adjusted scale of 1.011. Upon careful examination, you can notice a subtle but significant improvement in the model printed with the 1.011 scale. This minor adjustment from 1.012 to 1.011 has resulted in a more accurate representation of the original design dimensions. The right image illustrates how this fine-tuning of the scale enhances the precision of the model, aligning it more closely with the intended design specifications. We will explain how to read the over-extrusion values that can occur during the 3D printing process. To accurately determine the extent of over-extrusion, we utilize the deviation display mode in the slicing software. In deviation display mode, you can hover the mouse cursor over specific areas of the model to see the over-extrusion values for those particular parts. This slide presents the difference in over-extrusion values based on the viscosity of the resin used in 3D printing. On the left side of the slide, we see the results of using high viscosity resin, while the right side displays the results of using low viscosity resin. This visual comparison clearly demonstrates that higher viscosity leads to an increased amount of over-extrusion. It's important to note that higher filler content in the resin can increase its strength, but it also raises the viscosity and may reduce the reproducibility of the print. While using low viscosity resin is advantageous in reducing over-extrusion, achieving a balance between low viscosity and sufficient strength presents a challenging task. Therefore, selecting the right resin to balance strength, viscosity, and accuracy is crucial in 3D printing. In this section, we will discuss a common mistake often made when attempting to solve the problem of over-extrusion in 3D printing. Frequently, users opt to reduce the exposure time as a solution to overextrusion. However, this approach may not always be the correct course of action. The first image at the top shows a crown printed with a precisely measured exposure time of 7.5 seconds. This image illustrates the presence of overextrusion issues in the crown. The second image at the bottom displays the result of a crown printed with a reduced exposure time of 5.0 seconds. At first glance, this appears to resolve the overextrusion issue. This image illustrates the stability issues that can arise when reducing the exposure time in 3D printing. Lowering the exposure time can significantly destabilize the printed dental prosthetics, potentially leading to print failures. This is particularly crucial when producing precise dental restorations using 3D printing technology. While initially reducing exposure time may appear as an effective solution to overextrusion problems, this approach can ultimately degrade print quality and lead to other issues. Specifically, too short an exposure time can prevent sufficient curing of the resin, negatively impacting the strength and durability of the printed crown. This image showcases an experiment in which various thicknesses of pillars and structures with different loads were printed using different exposure times in 3D printing. The purpose of this experiment was to investigate how exposure time affects the stability and integrity of 3D printed objects. The image illustrates an experiment with 3D printed pillars and structures, each printed using different exposure times. On the left side, pillars and structures printed with a 7.5-second exposure time show a single failure, while the right side, printed with a 5.0-second exposure time, exhibits about half of them failing. This visual representation clearly demonstrates that too short an exposure time can prevent sufficient curing of the resin, leading to weakened structures. Based on the results of the experiment shown, we do not recommend reducing the exposure time in 3D printing. As observed in the experiment, shorter exposure times lead to an increased failure rate in the printed structures, primarily due to insufficient curing of the resin, which weakens the strength and durability of the objects. Too short an exposure time negatively impacts the physical properties of the printed objects, ultimately degrading the print quality and potentially failing to meet user requirements. Therefore, instead of simply reducing exposure time to solve overextrusion issues, it is important to consider a comprehensive approach that involves other factors. The image provided explains the feature of overextrusion compensation in slicing software. For 3D printing, it visually demonstrates how overextrusion compensation can adjust the internal and external dimensions of a print by specific amounts. This feature, available in certain slicing software, allows for fine adjustments to ensure that the printed object meets the desired dimensional accuracy. In the image, you can see that adding a positive value to the A parameter results in the reduction of the size of internal holes, while a negative value enlarges them. Similarly, for the B parameter, a positive value increases the external size of the print, and a negative value decreases it. The first crown at the top was printed with an expansion scale of 1.011 without applying overextrusion compensation. It visually represents the presence of overextrusion issues. The second crown at the bottom was printed with the same expansion scale but with overextrusion compensation applied. This crown shows resolved overextrusion issues, indicating the effectiveness of overextrusion compensation. However, it's important to note that both crowns still exhibit errors in the occlusal surface, highlighting the need for further adjustments in this area. In this section, we will discuss considerations beyond profile modifications that can address issues, especially in complex areas like the occlusal surface, which may not be resolved through profile adjustments alone. While profile settings in 3D printing are important, they are not a panacea for all problems. Particularly for objects with complex geometries or intricate details, additional strategies are required. One of the key methods to address these issues is by adjusting the printing angle. Modifying the printing angle can enhance the need for support structures, improve the strength of the print, and increase the accuracy of fine details. Adjusting the printing angle to optimize stress distribution in specific areas or to minimize the use of support structures can be an effective strategy. Modifying the printing angle is the process of setting the output orientation when creating an output program in a program that works with the printer before printing. An important point is that it's advantageous to place supports on the non-functional cusp side. For the upper jaw teeth, the non-functional cusp is located on the buccal side, while for the lower jaw teeth, it's on the lingual side. Therefore, it's recommended to install supports in these areas. Following this guideline, the process of adjusting the printing angle of a crown model using 3D printing software involves loading the model, using the rotate or object rotation feature to adjust the model's orientation, and the user inputting the desired angle values on the x-axis or y-axis as needed. Subsequent steps include creating support structures and slicing to optimize the printing angle of the crown model and enhance the overall print quality. This slide presents the results of printing at various angles. It was observed that the outcome at a 45-degree printing angle appeared to be overall superior, including in terms of the occlusal surface. This demonstrates how adjusting the printing angle can achieve desired results. Based on the previously explained methods of using profiles and additional information to print dental prosthetics as desired, we will now explore how effectively this approach can be applied when using different equipment and resins. We'll apply the previously significant factors of scale and printing angle to new equipment and resin, assessing their impact on the outcomes. This process includes the following steps. 1. Adjust the basic settings for the new equipment and resin. 2. Apply the established scale and printing angle for test prints. 3. Evaluate the quality of the printed prosthetics and compare it with results obtained using the previous equipment and resin. 4. If necessary, fine-tune the scale or angle to achieve optimal results. We found that by adjusting the scale and angle, similar improvements in print outcomes could be achieved across different printers. Notably, the printer's functionality to automatically adjust the exposure time for each layer thickness worked effectively. Additionally, the absence of over-extrusion in the prints was particularly impressive. As we conclude the lecture, we draw the following conclusions. 1. Setting precise exposure times for each layer is crucial. It ensures optimal curing and detail accuracy in the printing process. 2. Adjusting the scale to compensate for the shrinkage occurring during the polymerization process is necessary. This ensures that the dimensions of the final product are accurate. 3. Using materials and printers that minimize over-extrusion is important, and proper compensation should be made if over-extrusion occurs. This helps in maintaining the quality and precision of the print. 4. The printing angle significantly impacts the final result, so it is essential to identify the optimal settings for each specific case. Understanding how different angles affect the outcome allows for more tailored and successful prints. These key points underscore the importance of precision and customization in the 3D printing process, especially when it comes to dental prosthetics, where accuracy and quality are paramount.
Thank you for sharing all your tips with us, Dr. Kim.
Yes, I hope many clinicians have gained on understanding of key factors in 3D printing profile validation and achieved a perfect prosthetic fit.
Yes, for sure. So let's move on to Q&A sessions. So today we have 5 questions in total. So let's start with the first question. Question number 1. Do you think owning a printing machine in a clinic is a good idea? If I happen to own a printing machine, what would be the best way to utilize it?
Having a printing machine in clinic can be a great asset, especially if you focus on its optimal use. It's advisable to dedicate one type of material to each printer to maintain consistency and quality. Starting with a budget-friendly printer that is well-suited to your specific needs can be a cost-effective strategy. In a clinical setting, such a printer is extremely useful for producing items like dental guide stands, laminate cervical image, temporary crowns, splints, and even temporary dentures. These applications not only enhance clinical efficiency, but also improve patient care by providing swift and customized solutions.
Okay, so question number 2. Is there any precautions when restoring 3D printing liquid?
When restoring 3D printing leakage, especially those intended for dental prosthesis, it's important to handle them with care due to their different properties compared to traditional materials. While 3D printed items may not match the strength and adhesive qualities of conventional dental materials, proper technique can significantly enhance their quality. It is recommended to print with high precision, ideally at a fine resolution of around 20 micrometers. Additionally, adequate post-curing is crucial to enhance the stability and durability of the printed objects. This careful approach in handle and processing of 3D printing leakage is key to achieving satisfactory results in dental restorations.
Okay, question number 3. There might be many factors that can cause a misfit of a prosthesis, but which factor do you think is the most crucial that ruins the fitness of the prosthesis?
One of the most significant factors leading to a misfit of prosthesis is a viscosity of the printing material. Higher viscosity can restrict the flow and spread of the material, leading to inaccuracies in a final product. Therefore, it is imperative to carefully consider the viscosity of the material when selecting it, as this is essential for improving the quality and fit of the prosthesis. Additionally, other important aspects to consider include the scale of the print and the angle at which the prosthesis is printed. These elements play a critical role in ensuring the precision and proper fitting of the final prosthesis pieces.
Okay, question number 4. Is there any clinical tip or recommendation when polishing a printed crown?
To ensure that a 3D printed crown is of sufficient quality to be used as a final prosthesis, it is crucial to print it a high resolution, ideally around 20 micrometers. This high resolution helps in achieving a smoother surface, which is closer to desired final quality. For the polishing process, instead of using traditional polishing balls, it is recommended to apply a glazing. This coating can enhance the crown's smoothness and finish, offering a more refined and aesthetic pleasing result.
Okay, question number 5 is the last one. So, have you ever found the fitness difference between milled and printed crown? Do you think we can restore pre-knitted crown as a final one?
There is actually no significant difference in fit between milled and printed crowns. Following the manufacturer's recommendations for printing might not yield a product suitable for use as a final prosthesis. However, with the adjustment and fine-tuning outlined in this lecture, you can achieve significantly improved fit with printed crowns. As for using them as final prosthesis, the precision and fit of the output are generally not the issues. My hesitation in using printed crowns as final restorations primarily stem from concern about their strength and adhesion properties, which I believe still require further evaluation and improvement.
Okay, that was the last question. So that's all about it for today. You'll be able to watch this webinar on our YouTube channel and Medit Academy once it's completed. Thank you for being here, Dr. Kim.
Thanks everyone for joining us today. Hope to see you at our next webinar. Bye.
Bye.